Stronger than steel, lighter than aluminum, it begins as air turned into structure, but it can still shatter steel in a single strike. Everything starts with a volatile liquid under extreme control. One impurity can destroy the final material. We force polymers through microscopic holes to align their future strength, but now they face fire-level heat. At 300 degrees C, the fiber begins its irreversible transformation. One wrong degree turns it into ash, a dangerous liquid stored under extreme cooling control. One spark could erase the entire plant. We trigger molecular chains to build structure from nothing, but speed decides strength or failure. We remove every impurity down to microscopic levels. Hook. Because dust becomes structural weakness. Liquid becomes solid fiber in a fraction of a second, but it is still too weak to survive. We stretch fibers to align molecular structure perfectly. Stretch too far and everything snaps. Heat prepares the fiber for its final transformation. This is the last moment it stays soft. Tension is controlled at microscopic precision. One mistake destroys the entire batch. Fibers enter the furnace, white turning into black. Now chemistry begins rewriting reality. Oxygen is removed so carbon can survive extreme heat. Inside here, air becomes deadly. At 3000 degrees C, atoms rearrange into perfect carbon crystals. But perfection has one weakness. We roughen the surface so bonding becomes possible. Without it, nothing can ever stick. Oxygen-free chambers protect carbon from burning away. Even air is now the enemy. Impurities are violently expelled at high temperature. Purity comes at a cost: fragility. Carbon crystals lock into extreme structural strength. But cooling failure means total collapse. Toxic gases are neutralized during transformation. Waste here is more dangerous than fire. Molecules align into perfect crystalline order, but smoothness makes bonding impossible. Electricity etches microscopic grip into the surface, too deep, and strength is gone. Protective coating preserves fragile carbon structure. Without it, fibers collapse instantly. Heat stabilizes fiber for safe handling. Now it is ready for human hands. Thousands of fibers combine into massive structural threads. One tangle destroys everything. Resin binds fibers into aerospace-grade material, but now it has a ticking clock. Cold storage pauses chemical reaction temporarily. Time is now the real enemy. Clean rooms eliminate microscopic contamination risk. Even a hair becomes catastrophic. Humans guide precision where machines cannot. One error destroys the structure. Special tape seals vacuum pressure perfectly, but even seals can fail under stress. Breather layers allow trapped air to escape. If it stops breathing, it dies. We detect leaks smaller than human hearing, 60 seconds to stop failure. Sensors monitor internal temperature of material. Now chemistry becomes uncontrollable. Autoclave simulates ocean-level pressure. Once closed, there is no escape. Nitrogen replaces oxygen to prevent combustion. Pressure now exceeds deep-sea survival. Resin flows and binds fiber completely. If overheated, it boils from inside. Liquid resin transforms into solid structure. Now it becomes aerospace armor. Cooling must be controlled to prevent cracking. The danger begins after the fire ends. Pressure is released after full curing. Now we discover if it survived. We unwrap the finished carbon fiber structure. Looks perfect. But is it? Part is separated from its mold carefully. One crack can ruin everything. Diamond tools cut through impossible hardness, but one slip destroys the part. Carbon dust is captured before it spreads. If it escapes, systems collapse. Water jet cuts carbon without heat damage, but edges hide invisible weakness. Edges are sealed to prevent delamination. Miss one point, and it fails. Titanium inserts distribute extreme loads, wrong metal, and chemistry destroys it. Bond thickness is measured microscopically. Too thick means total failure. Lasers guide perfect structural alignment. If laser fails, mission fails. Special adhesive bonds structural components. Clock started. No stopping now. Hydraulic clamps apply massive pressure. One clamp failure ruins everything. Heat curing happens outside autoclave. This is the most dangerous stage. Surface is measured at microscopic detail. Too smooth means coating failure. Robot sand surfaces with perfect consistency. One mistake destroys strength. Solvents clean every microscopic contaminant. Even sweat becomes a defect. Primer prepares carbon for final coating. Now the miracle is hidden. UV light reveals hidden surface cracks. One crack changes everything. Ultrasound measures exact material thickness, too thin or too heavy. Both fail. Balance testing ensures perfect rotation. Even 1 gram becomes deadly. Carbon safely conducts lightning energy. If it fails, explosion follows. Vacuum tests confirm internal integrity. No movement means survival. Every part has complete traceable history. Now it faces real-world risk. We push the structure beyond its maximum load limit. At 10 G, it still doesn't break. Extreme temperature shifts test molecular stability. Heat and cold are trying to tear it apart. We listen for hidden internal structural cracks. One silent crack means total failure. Every part receives its unique identity and record. Now it becomes a certified aerospace component. X-rays reveal what the human eye can't see. One invisible gap or instant scrap. Sensors detect microscopic stress before failure. The material is already screaming. We bend the wing beyond flight limits. It bends, but refuses to break. Fracture analysis reveals how failure begins. Even perfect parts have hidden weakness. We measure thermal behavior under extreme heat. 2% error can melt performance. We test how layers separate under pressure, because layers always try to escape. We expose material to corrosive salt environments. Even carbon has chemical enemies. Lightning strikes test survival of aerospace structures. One strike can destroy everything. Hardness testing reveals hidden weak spots. One soft point, hidden disaster. Lasers align rotating components with perfect precision. Micron error means engine destruction. Final human inspection decides approval. Machines say yes, but humans decide risk. Robots build aircraft structures at extreme speed, but speed hides global supply risk. Carbon fiber survives crushing deep-sea pressure. One flaw at depth, routers instant collapse. Wind blades grow longer for maximum energy capture. The longer it gets, the more powerful it becomes. Carbon fiber restores human motion in prosthetics. It returns energy like a living tendon. We stretch material toward space exploration dreams. A ladder from Earth to orbit is possible. Multi-axis braiding creates seamless structures, but extreme heat still tests perfection. Satellites rely on carbon for perfect stability. 1 micron shift breaks global systems. Brakes survive extreme friction without melting. Speed becomes heat, but it survives. Hydrogen tanks store explosive energy safely. 1 leak or a revolution. Space radiators release heat into vacuum. Without this, spacecraft would burn itself. We recycle carbon from old aerospace parts. Waste becomes the future again. F1 chassis protect drivers at extreme speed. It breaks so the driver survives. High-altitude drones fly for months non-stop. They become satellites without rockets. We build structures atom by atom in theory. The future starts at molecular level. From air to aerospace, this is engineering evolution, and this is only the beginning.